I'll talk about our paper when parts are greater than sums. Individual large language model components can outperform full models. First, I'll talk about previous work on prompting and in-context learning. Second, I'll share our findings after we look into the LLM internals. Finally, based on our findings, we propose an efficient and effective future learning method. So in this previous work, the authors find that even recent large language models are still sensitive to prompt template. For example, if we are lucky and choose these templates, we can get pretty good ICO accuracy. However, just slightly changing the template, we can get very bad task accuracy. Similarly, in this paper, the authors show that there are no universally well-performing templates. This means that it is not easy to understand or explain ICO through prompt engineering. So what if instead of focusing on the prompts, we look inside the models? Basically, we want to know that across different prompts, is there some consistency inside the large language model? Here we define a prompt as a sequence of k-templated examples. So how do we study the internals of large language models? We know that a transformer block consists of multi-head attention block and a MLP block. And based on this paper from Anthropic AI, we can break down the multi-head attention into the sum of all the heads in this data. So we can view the residual string as the highway that directly carries the contributions of every attention head and every MLP to the output logits. In this paper, we define components as everything that writes to the residual string, including the initial hidden state, the every attention head, and every MLP. And in our paper, we show that we can further decompose the layer norm and derive a formula that the output logits is equal to the sum of the contribution of every component. Note that this is a mathematically equivalent formula for the model's output logits, and the decomposition itself does not require any training. Now we have broken down the LLM output into simple additions. What can we do next? Let's compare with the standard view of in-context learning. So in the standard ICL, we use the entire model to make predictions. We take the logits and do argmax over all the possible label tokens of a classification task. Now, with our decomposition, we can study how each component performs. For example, we can get the prediction of component J using its contribution. This is a real example. The model is Llama 27B for SHA ICO on AG News. Under this specific prompt, the full model performs poorly, lower than 0.4 accuracy. And we show that we show how individual component performs in the figure, where each grid is the accuracy of a component. First, we find that there are good performing components, even when the full model performs poorly. For example, here are some components that can perform higher than 0.7 accuracy. At the same time, there are plenty of bad performing components inside the models. Like here, these components do much worse than chance. Here are the quantitative results across 8 classification tasks. The pink bars are the accuracy of the full model, and the blue bars are the best performing components in each task, and the gray bars are the worst performing components. So we show that inside the model, there are components that individually do well or do poorly. And the top one components, the blue bars here, sometimes even outperform the full models. In this figure, the model is Llama 2 13B. We also show similar findings on Llama 3 and Mistral Instruct. Our second observation is that components perform consistently across prompts, even when the full model accuracy changes dramatically. Like here, the two slightly different templates give us totally different full model accuracy. But if we compute the correlation between the component accuracies, that is, we flatten these two matrices into two vectors and compute the Pearson correlation, we can get the correlation as high as 0.81. Here are the quantitative analysis of consistency under different settings. The first settings is that we sample two sets of demonstrations with a fixed template and measure the correlation in their component accuracy. The second setting is that we fix the demonstrations and sample two templates from prompt source and then measure the correlation. In the third setting, we also fix the demonstration and change the templates. But here the templates are a pair of curated templates that are very similar to each other, but lead to very different accuracy. This is basically the idea of contrast sets, but on prompt templates. So we find decent correlation in the first and third settings. The yellow and the green bars here. But in the second setting, the correlation is much weaker. The blue bars here are much lower. This means that components behave similarly under different demonstrations and similar templates, but the similarity decreases as the templates diverge. In addition to these three settings, in the paper, we also show the transferability of components across datasets. Let's move on to our fuchsia learning method. So we have observed good and bad performing components inside LLMs. What if we do some kind of reweighting by assigning a scalar weight on each component? Um, so we use fuchsia examples to train the weight while freeze the entire LLM. Our loss consists of two terms. The first one is just the standard cross entropy loss on the classification task, and the second term is the L1 regularization to encourage sparsity on the weights. Let me talk a bit more about these fuchsia examples. Suppose that we have k examples, like k equals 12 or 24, just a few labeled examples. Now, instead of using all of them as the in-context examples, we can use 4 of them as the prompts and the rest to train the weight. Specifically, we run for-shell ICO on this training set dtrain and cache the contribution of all components. And then we can use this as our input features and train our weights W. In practice, after we cache these component contributions, we can discard the entire LLM and train a linear model on a CPU in 1 minute. So our training is very efficient. How does our component reweighting method work at test time? First, we run for-shell ICO to get the component contribution. And then we plug in the learned weight. And then we can get the logits, and we do argmax to get the predictions. In practice, our method has little computation overhead over four-shot ICL. Here are the results. The accuracy is averaged across tasks, and the numbers in the x-axis means the number of labeled data. We can see that in standard ICO, when we increase the number of demonstrations from 4 to 24, there is not much gain in accuracy. In comparison, our component reweighting method, the blue bars here, can better utilize the same labeled data, achieving much higher accuracy. Also, our inference speed is much faster than the standard 12-shot and 24-shot ICO because our component reweighting method always runs similar to 4-shot ICO. We also compare our method to two baselines, the green bars here, and we show that our method performs the best. Our method also performs the best on average on Llama 3 and Mistral Instruct. Please see our paper for more information. In summary, we share a new view of inconvex learning by decomposing the large language model output into the sum of model components. We identify curious components and reveal consistency inside the model across prompts. Finally, we propose an efficient few-shot learning method by reweighting the components. Thank you.